Welcome everybody out there in TV land. This is the Friday RAMCloud show. And today's topic is the RAMCloud RPC architecture. Actually, I'm going to focus on the client side of the RPC architecture because that's where most of the interesting and more complex stuff is. So first, let me talk about the goals we have for our RPC system. By the way, I would say this is an example of code. There was absolutely no way we were going to get this right the first time because the requirements of this are so complex and interrelated that I think there's no way to put together a working RPC system with all the right attributes. So we ended up, putting something together initially that didn't do the stuff that I'm going to put on the goals list very well. It was kind of haphazard, and then got a whole bunch of RPCs implemented. And then by going and looking at all of our RPCs, seeing all the implementations we had, then it was possible to think back about this and come up with what the right structure is. But I don't think there's any way. I know I couldn't have done it a priori. So this is one of the reasons why I think you got to plan on implementing complicated things twice. Once is really just a data collection mode to figure out what the real problems are, then do the real implementation. So goals. Actually, let me put that here so I can slide it out of the way. First goal of our RPC system is we wanted to support many underlying transports. That is, transports are the things that actually communicate over the network. Since we're worried about low latency, we want to be able to experiment with different kinds of networking technologies or different underlying protocols. And so one of the key goals is to have this transport mechanism where people can build these, and then all of the other RPC infrastructure, all of the details about doing, create table and read object and write object, all those things have to be completely independent of the underlying transports. So we can plug in new transports anytime we want to try out new networking stuff. So that's the key thing, and this division between the RPC layer and the transport layer is a really important one. We want a really simple API there. Second thing is that the design of the RPC system has to be consistent with the idea of low latency. That is, we need some mechanism that, for example, it better not have a whole lot of layers. If the structure gets too complicated, and kind of verging on that with what you're going to see here, that could end up impacting our latency. And one key thing about this is that it has to support polling. That is, we don't want to put a thread to sleep when it's waiting for RPCs because we're talking about completion times of RPCs of only a few microseconds. But by the time you put a thread to sleep, you need to wake it up again, and you would already have lost valuable time. So for our simple RPCs, an application will just sit in the loop waiting for the result. So the architecture has to support that. Yeah?
Do you think that if you had designed the RPCs for not supporting many transports, say for a particular one, could it have been faster or much better in some other way? Like, did you have to give up something for that?
So the risk is that by adding these layers, we've hit latency. And we've hurt our latency. Pardon?
Repeat the question.
Oh, yes. Thank you. Did it cost us something to support many transports? And my guess is probably I think you'll see the API is actually pretty clean. So in that sense, I think it worked out well. It may well have hurt us on latency. And I have to say, of these goals, I think latency is the one that, ironically, we've spent the least effort on so far. We've tried to get, particularly me, I've tried to get all the other stuff right. And so I suspect there's some things we've done that have increased latency unnecessarily. And the next step, which I hope some of you will be looking at, is to re-examine all of this infrastructure to see if we can improve the latency significantly. All right, the next thing, this is one of the things that has evolved a lot since the early days of RAMCloud, which is we need a modular retry mechanism. Let me see if I can explain what that means. So the first thing is that every RPC, yeah, sorry, that door is going to be buzzing probably every 15 minutes. I have to pull the door closed. Sorry out there in TV land. Momentary pause while we get the door shut. Okay. Let me wait for Colin to come back again. Every RPC may potentially need to be retried. And it may need to be retried at several different levels for many different reasons. So let me give some examples of the different kinds of retries we have to support. One obvious one is if a server or the coordinator fails. Then we have to retry the RPC. And by the way, when we retry after a server failure, we may have to send the new RPC to a totally different server. And in fact, it may even use a different transport to get there, because this other server may only support some other kind of transport. So first of all, this tells you immediately we cannot do the retries entirely within the transport level. And now initially we tried to do more of the retries in the transport level, but the problem with that is that also then you end up re-implementing the retry mechanisms over and over again in every transport level. So one of the key ideas of this design is that the retry stuff is all implemented in exactly one place. Centralized, it's going to be this mess of blue classes here that I'll talk about a little bit later on. Okay, so that's when issue server failures. Another one is that servers may request retries. So you send an RPC to a server and it says, for various reasons, I can't do it right now, please retry. And one example of that is if you send a write request to a master and its memory is totally full. Say it's waiting for the cleaner to run, or maybe it's even run out of memory space. It may ask you to do a retry because there's no more space. Another example is when a server first starts up, if it receives a request before it is finished initializing, it'll ask you to retry. One of the thoughts in both of these things is that when a request has to delay for a while, over time we've realized it's better not to have that request wait on the server with resources allocated on the server. It's better just to unwind everything on the server, send it back to the client, and tell the client try again in a millisecond, whatever, so that we're not holding resources on the server while we're waiting, because if we do that, that can cause deadlock. But there are other reasons also. Another example of a server-requested retry is if a client sends a read request for a particular object to a particular server, and the server doesn't actually store that object. So when this happens, the server will send an error back to the client, and then the client will see that error and realize, oh, I must have an error in my cache of location information. And so we'll flush its cache about where the objects are stored. It'll go back to the coordinator, ask the coordinator again, where is this object really now? And then the coordinator will tell it, and then the client will retry, probably to a different server. Yeah, Ankita.
From the point of view of the server, why are these retries? Why are they not just error messages?
From the point of view of the server, why are these retries as opposed to error messages? Well, actually, this one is just an error code. And in fact, these others are all, they actually are implemented as return status values in the RPC that have a particular error number. But the consequence of those is to do retries. And then the last example of retries is network issues. Lost packets and stuff like that. So many of those can be handled down inside the transports. And in fact, they are. Transports will automatically do some level of retry. But it's actually really convenient if a transport starts feeling confused about itself, it can just reject a request, just sort of log an error, and it will get retried at a higher level. That's what will basically, as you'll see, the higher level software will simply throw away the session, open a new session, and try again. So it's a convenient escape hatch for errors that don't happen very often. Rather than handling itself, a transport can just reflect an error upwards, and then the thing will automatically get retried. So some of the goals for this now, these are some of the problems. We want to implement the retry stuff centrally. For example, in the first version of the RPC system, if the read RPC sent a request to a server and it got back this error saying object not here, there was code associated with that read RPC that would detect that and then retry. Then the problem is we have to also put code in the write RPC and the delete table RPC and all those things. So the goal is to have the code that handles this situation. We want exactly one copy of that code. In fact, you're going to see it's in here. It's going to be in fact, it's going to be in this wrapper class. And it works for every RPC. that can have objects that move from one server to another. So we want to implement this centrally. And then it turns out that there are groups of related RPCs for retries that have similar behavior. Like, for example, all of the RPCs that operate on an object, they have to go to the server for that object, and it's possible that somehow the system configuration could have changed and the object is not going to be there anymore. And so we want to have somehow be able to group RPCs very naturally so that they share all of this retry code. And so you're going to see that all of the RPCs that manipulate an object are subclasses of, they have objects that are subclasses of this one wrapper class that will handle this particular retry condition. And then, let's see. And another example is all of the retries that talk to the coordinator. So the coordinator could crash, and a new coordinator could start up on a different machine. And so we need a mechanism for those RPCs to find the new coordinator and send the RPC over to that coordinator. Well, that's all going to be handled here in this wrapper class, and all of the RPCs related to the coordinator making coordinator requests will go through that path. So it's shared. And then the third thing about retries is sometimes we don't want to retry right away. We want to wait. Like, for example, if we're in a situation where there's a big overload, rather than, if a server's overloaded and it's trying to shed load, you don't want to immediately come back and ask again. Are you feeling less busy now? No. Are you feeling less busy now? Would you shut up and go away and let me get some work done? So the server can send back information saying, please retry, but not for a while. In fact, it can say, please pick a random number between 1 millisecond and 10 milliseconds and retry after that much time. And then the client will do that and come back later. Okay, and then finally the last goal is that, and this was the one that really had us just twisted in knots initially. Oh, yeah.
Do we have a generalized exponential backoff method for retries?
Do we have a generalized exponential backoff method for retries? No, but we could easily implement one, and the good news is you only need to implement it here, and it can immediately apply to all RPCs. It's right now it used to be it was a constant time backoff, and then I modified it so it could be a random number within a range, but if exponential makes more sense, I've occasionally wondered about that. The good news is we've got a place where we can easily fit that into the system.
Would this typically be used if a server is recovering, or do we expect this to happen even otherwise?
Would this be used? Question is, would this be used when a server is recovering, or in other situations? The answer is yes, certainly in that case, and I think there are other cases also. Like if a server is under really gross overload, you might want to tell people just go away and come back in a millisecond. Okay, then the last constraint is that every RPC must have an asynchronous version. And again, when we first started building the RPC system, we wrote asynchronous versions of the RPCs. At the top level, individual RPCs would be asynchronous, and they'd have special code in them, and it just doesn't scale. Okay, so I'm going to first give you a walk through this architecture, and then I'll talk about what the interface to clients looks like at the highest level, then I'll start going through these classes. But first, Benham? If every RPC I had to have special code for making that RPC asynchronous, it just means I've got this code for asynchronous stuff just duplicated all over the place. And so it bloats the amount of code in every RPC. Just like if I had to have extra code in every RPC to do retries. So you're going to see these top-level RPCs have almost nothing in them that has anything to do with asynchronous operation. There actually is a little bit, but it's just a matter of how they're structured in basically two different pieces rather than one monolithic piece. But in terms of code, hopefully you'll agree it's really simple code. Okay, so the class hierarchy you're going to see here is that at the bottom we have all the transports. And the transports get invoked from kind of all over the stuff above. There's a very simple interface here I'll talk about. And then there's a collection of classes above that this whole thing I call the wrappers, all the way from the blue all the way up through the red. and it's a 4-level inheritance hierarchy. So that's a lot more levels of inheritance than you'd normally like to have. And what I would say about this is that the layers on this hierarchy, there's not a lot of information hiding there. That is, if you're working inside object RPC wrapper, you basically have to know how RPC wrapper and RPC notifier work. So there's not, the reason for the layers of inheritance is to cut down on code duplication. But these classes are pretty tightly, so at least any vertical path through here is pretty tightly entwined with each other. So that's a downside. I would have preferred not to have this, but given the problems we had to solve, I wasn't able to come up with a simpler structure than this. So if you have ideas, that would be interesting. And the idea is that various classes here encapsulate various things. You're going to see that RPC wrapper is actually the class that does most of the work, and then these other classes specialize it slightly for various groups of RPCs. And then you're going to see there's one class for every specific RPC. So there's a class for the create table RPC and a class for the read RPC and so on. Ankita.
Why is RPC notifier and RPC wrapper separate classes if there is no information splitting there? Like on the
why are RPC wrapper and RPC notifier separate classes? They almost don't need to be separate classes. RPC notifier just has almost nothing in it. It's a pure virtual class with only 2 methods. The reason is that this is the only thing that transports need to know about the wrappers. So as you'll see, this is what transports know about. And so I put that in a separate class to be clear that transports do not need to know about anything above that level. And actually, this is not really a cause for, this won't be a source of complexity because this particular class is so simple. It has almost nothing in it. The more complicated thing is understanding the relationships between RPC wrapper and the classes above it. Those are more intertwined. Other questions so far? Okay, how about push the goals out of the way and push the diagram out of the way. Bring a new board in. Okay, so now let me talk about if you're a client application, how do you use the RPC system? And it's a pretty uniform way across all the RPCs. So that's the code above the red level that's going to actually, if you're writing an application, you want to invoke RPCs. And when I say client, I mean both what you do in an application and also if you're writing code in a RAMCloud server that's going to invoke operations in other RAMCloud servers, you would use the same mechanism. So the server-to-server APIs are the same as client-to-server APIs. So first, for each RPC, there's a method that invokes the RPC synchronously. And I'm going to use, as an example, I'm just going to use create table. So for example, create table, it returns a uint64t, that's the identifier for the table that was created. And you invoke it with a name. And then if you want it to be spread across many servers, shoot, this overflowed my line. I believe it's, you get a server span. In which case the server will, the coordinator will spread the table across that many servers to begin with, divide up among that many servers. And yeah, so it's just the RPC method is just a method that looks like any other RPC. It will invoke the RPC and it will not return until the RPC is complete. So these are always synchronous. Then in addition, there's a class for each RPC. And this is what provides the asynchronous interface. So the class name can be sort of translated by a computer from the name of the method. It's immediately derived from that. So the create table method, there is a class that is the same as that, except that the first letter is capitalized, and there's an RPC suffix on it. So there's a create table class that's used for the create table RPC. And the constructor takes the same arguments as the synchronous method and starts the RPC. So if you construct one of these RPC objects, it will initiate it, send the request, start it running. But the constructor does not wait for the RPC to actually finish. So it's asynchronous. So in this case, you could say, for example, create table RPC, create RPC, and then give it, well, actually, you have to give one additional argument, which is the RAMCloud object corresponding to your whole cluster. That's the object on which you would normally invoke the method there. So you give the RAMCloud object, and then you give a name and the server span. Okay, then once you've done that, then there are other methods you can invoke on this object. Do kind of obvious things. So for example, there's a wait method. So if you invoke a wait on the create RPC, then it will wait for it to complete, and actually it will return the same thing that this method returned. It will return the ID of the table that was created. You can invoke a method isReady. This will check to see whether the RPC has completed, but it won't wait for anything. So if the RPC is not finished, it'll just return false, and you carry on. And then there's a method cancel you can invoke that does what you guessed. It aborts that RPC, or does the best it can to abort the RPC. It's possible the RPC is already finished by the time you call cancel, so it will not unwind or undo the RPC. The RPC may or may not actually have finished if you cancel it, but the idea is that at this point, everything on this machine can start discarding resources for that RPC. The transport can clean up and so on. So it's possible the RPC cancel will not attempt to contact the server and stop the server from doing anything. So if the message has already been sent, the server will probably finish doing the RPC. Yep, Venom.
Does this cancel method go inside the transport and drop the packets that are coming for that RPC?
Does the cancel method actually notify the transport? And the answer is yes. That will actually call into the transport and tell the transport it should stop working on that RPC and drop packets associated with it and so on. And by the way, if you delete this object, that implicitly cancels the RPC. Questions so far?
When you say delete the object, you mean when the destructor is called in any way, either explicitly or implicitly?
Yes. So if you can hear it to you, yes. The question was, does that mean delete in any way? Like as long as the constructor is called either implicitly or explicitly, will it do the cancellation? The answer is yeah. Ankita.
You seem to imply that writing the synchronous method generates the asynchronous class for you, but that's not the case, right? You have to actually explicitly write both.
The question is, does writing the synchronous method generate the asynchronous class for you? And the answer is no. No, when you build a new RPC, you have to create both this method and the class. And as you'll see what happens...
Want the asynchronous on something.
Pardon?
What if you don't want the asynchronous on a particular...
What if you don't want an asynchronous version of a particular RPC? That is not allowed by Rule 4.
Okay. It's not an option.
That's antisocial thinking. We stamp that out. We send you off into the countryside to work in a commune for a few years to re-educate you, and then you come back and you can try again. So, but as when you look at the code, what you're going to see is that the synchronous method is basically just an instance of the constructor followed by an invocation of wait. That's all it is. So there's nothing. In fact, internally, all of the RPCs are implemented with this object, with the asynchronous version, and then the synchronous is layered on top of that. Other questions about this? Okay, then one other thing, just added in here, which is actually pretty important, is that of these various methods on the RPC, the only one that will throw any errors is wait. That means in particular that the constructor, this method, may not throw an error. It must always succeed. Now, the way it can succeed, if there's an error, what it can do, as you'll see, is it can actually start the RPC and then immediately fail it So that in fact, there's no RPC ever sent. And as soon as somebody calls wait, then the error will be thrown. But this was important because otherwise we found when we were writing client code that was asynchronous, we'd have to catch errors in 2 different places for everything. And often it would be the same kinds of errors that could happen in both of these places. And so it just doubled the error handling code. There was no advantage, there's no extra advantage of catching an error when you create an RPC. Instead, if an error occurs, the RPC will appear to be complete, and then when you call wait on it, then you get the error. So that's another rule. If you're writing new RPCs, you're not allowed to throw errors in the constructor, only in the wait method, which means, of course, that the synchronous version can throw an error because it invokes wait. Benham.
But if you handle errors in like create RPC, then you're actually grabbing that error earlier, right? Because you don't have to wait for the error to come up.
The comment is if you say signal an error in the create, you could potentially deal with it sooner rather than later on, and that's true. But typically when people initiate asynchronous RPCs, they will find out, if the RPC is finished, they will find that out very fast. You know, typically, when you're doing asynchronous RPCs, you're also constantly checking to see if RPCs are finished. And so you'll immediately check and find it. So, you know, maybe it's a few microseconds or a few hundred nanoseconds before you find out. But the additional hassle of having to write code that checks in 2 places, the problem is that people forget to check in one of those places, and then you get bugs in your code. And so it's just, in general, you know, one of the things we've tried to do in RAMCloud is to concentrate errors. Try and reduce the number of places where errors can occur, and try and group errors together so that you have a smaller number of bigger errors rather than zillions of little errors that all have to be handled separately, because the complexity of that code just kills you. Okay, then I wanted to show one last thing, which is how, roughly how you might use the asynchronous mechanism. Let's see if I can do this without having to write a ton of code. But a common thing in RAMCloud is that there'll be pieces of code that want to issue several outstanding RPCs, and then they want to be able to figure out whenever an RPC finishes. So for example, you might do, you know, you sort of create one RPC1, suppose I would do for example, read RPC, RPC1. This is going to show a read operation, and that's going to have some arguments to read an object. And then I want to read several objects at the same time. So I start another one, and maybe another one. And then I'd like to do something whenever any of these finishes. So then what you do is you have a while loop. And in that side of the loop, you'd say if rpc1.isReady, then you'd invoke the wait operation on that. IsReady, remember, just tells you that it's done. After it really is done, you're supposed to always call wait. That sort of cleans everything up and logically finishes the RPC. And that's what we return any results, for example. You don't get any results from isReady other than a true-false indication of whether it's finished. So then I would do rpc1.wait and handle that however I wanted. And then, then I'd say, well, what if rpc2.isReady, and so on and down, if rpc3 is ready. And actually, when we do this, typically, a common case would be if we want to do a broadcast to everybody in the cluster, we'd decide, well, we want to keep some number of outstanding RPCs, and so we'd keep an array of outstanding RPCs, and when one finishes, we'd handle that, and then immediately start at the next one. So we kind of cycle through and eventually talk to every server in the cluster. Now, there's one thing missing from this loop, though, which Benham discovered about a week ago, which is if you did this, start the RPCs and check is ready and sit in the loop waiting for them to finish, none of them will ever finish. And the reason is that down underneath the RPC system, it's polling based. That is, the transport won't receive any incoming response messages unless you call into it and tell it to check. So the transports are used to a polling approach where somebody says, check and see if you got any messages. And then they'll check and see, and if so, they'll process them, and an RPC will eventually finish. None of these methods, so the wait method, sorry, wait will actually invoke the polling system, but isReady will not. It just checks to see if the RPC is done. So if you want to give the transports a chance to actually execute, you have to invoke the underlying polling mechanism in RAMCloud that will go through and, for example, tell every transport to check and see if it's got any incoming packets. And right now, the way you have to do that is you have to call, if you have your RAMCloud object, that's your handle for the whole RAMCloud, I think you have to call RAMCloud dot context, this is horrible, arrow dispatch arrow poll, I believe. And again, that just says, again, look around and see if any network packets have arrived, and if so, handle them. Sojin is going to, his job for his first project is to take this horrible mess, and actually that's going to be replaced with one method call where you just say RAMCloud.poll. It invokes the poller. But if you want to do asynchronous stuff, someplace in your asynchronous loop, you have to invoke the polling mechanism to look around. So call the poller, and then go back and see if anything finished because of that. Questions about that? Okay, and we have code like this in several places, like the serverless code in the coordinator that has to go and update everybody in the cluster whenever a server comes up. It has this loop where it keeps a whole bunch of RPCs outstanding at a time and eventually gets everybody updated. The masters, when they're doing backup operations, has little loops like this as well, where it sends out replication requests to backups to store backup copies of things. Yeah, Henry. Yeah, actually, the question is the wait function constantly calling poll? The answer is yes. If you invoke this, basically the wait function is essentially nothing more than checking to see if the calling is ready, and if not, then calling the poller and looping back around again. It's almost nothing more than that. Yes, Sojin.
Does wait function ever yield?
Does the wait function ever yield? No. The only form of yielding is it invokes the poller, so it will allow anybody that's set up to participate in polling to have a chance to run, but it won't let any unrelated third-party code run. We occupy the CPU continuously. I suppose you could imagine maybe if an RPC took a really long time, maybe you'd like to yield the CPU, but we don't do that right now. I'd say the solution is we should fix our RPCs so they don't take very long. Is there a maximum how much data? It's like 8 megabytes is the largest RPC. So that limits how much data you can get at once. That could take about a millisecond or two, a few milliseconds for that.
Yeah, you could get quite a few CPU instructions in that time.
Yes, you could get quite a few CPU instructions, but nope. Haven't looked at that yet. Okay, we good on this? All right, now let me talk about these interfaces with the transport. What the transport provides to the higher levels of software are these things called sessions. And a session is just an open connection to some other machine that's reliable, flow controlled, on which you can send requests and get responses back. So the basic APIs for that are, if you have a transport, you can invoke get session, and then you give typically a service locator. Service locators are these strings in RAMCloud that identify a particular transport name and a particular server, and so give you information about how to hook up with that server. So for the TCP transport, the service locator gives the host name and the port number, for example, for that server. And then once you have a session, then you can say session send request. And this takes 3 arguments. It takes a buffer that contains the request, a buffer that contains the response, and an RPC notifier. What will happen when you call send request then is that the transport will initiate the sending of this request to whatever server's at the other end of this session. And then when a response comes back, it's going to do something in this notifier that I'll tell you about in a minute. And if an error occurs, it will also do something with that notifier. And then the last interesting method is that there's session cancel request. And that takes a notifier. So a notifier is think of it as the stand-in for a request. That's what you use. That's the handle you have on a request. So when you start the request, you pass it a notifier. If you want to cancel it, you just say, if you've got a request around that relates to this notifier, kill it now. Yep.
2 questions. First question is the buffer class fixed size or is it variable size?
Buffer class will hold a variable size amount of data.
And if I pass the same buffer for request and response, is that going to cause an error condition?
Question is, if I pass the same buffer for request and response, will that cause an error condition? No one will detect an error, but I suspect that it is inadvisable.
Because it seems like it'd be an efficient way to reuse memory.
That this could be efficient to reuse the same memory? Yeah, except that transport can feel free as its very first step is to clear the response buffer, which might be undesirable if you're then going to use that as the request.
Where does this session opening happen? Because before you can.
Like where do you call get session? Yeah. Let me wait 1 second for Anka to come back. Actually, I'll start writing. So sessions are typically managed outside this whole structure. There's various classes that manage sessions, and they will typically keep caches of sessions so you don't have to. So for example, if you're communicating over and over again with the same server, you don't have to make a new session every time you send an RPC. And so the places where they're cached right now, there's 3 places. One is in the server list code. So server list is a class that keeps track of all the servers in the cluster. And so it will keep a session for each of those servers. So when servers are communicating with each other, they just use the session associated that the server list manages. There's a class called Object Finder, which Ashish has been getting familiar with. Object Finder is used on clients in order to find the server that knows about a particular object, a particular table and key. And it keeps information. Actually, it works together with a class called Transport Manager, but it keeps information about those sessions. So when you want to have a session to the server holding a particular object, you call Object Finder, and it'll give you one. And then the third one is Coordinator Session. And this is a class that maintains exactly one session. It keeps a session to the current coordinator. If the coordinator crashes, it'll find a new coordinator, open up a new session to them, and so on. Okay.
Does the session expire only when the server associated with the session crashes?
Does the session expire only when the server associated with the session crashes? No, it can expire. It could expire any time. It doesn't really matter. That would only affect performance. If you expire your sessions rapidly, then that could make things slow because you're having to constantly reopen sessions. But if a session fails, I'll talk about that in a second, higher level software will automatically open a new session and try again. So there's no fundamental harm in a transport expiring a session.
It could be timeout-based in that case.
However it wishes. Yeah, if a session's idle for a long period of time, it could just expire it if it wants.
What do we have right now in RAMCloud?
What do we have right now for doing that? I think we have a hodgepodge. I'm not sure that we consciously cancel sessions anywhere. We probably should. Maybe this is why we should try and meet in 4:15 rather than here. So okay, so the sessions are typically cached. Now, these are the methods that the higher level software uses to talk to the transport. Now the question is, what does the transport do to talk upwards, in particular when RPC is complete, or if there are problems and RPCs fail? And the answer is that that's done with this RPC notifier object. So the transports, once they accept a request, they promise that they will eventually invoke one of two methods on RPC notifier. And the two methods are completed, failed. These methods take no arguments, they return no results. They just indicate, so completed, obviously that means the RPC succeeded, at least in the sense that we got a response back. The response may actually contain some error information from the server. We'll have to look at that later on, but it means that we at least did manage to get a request over and the server processed it and it sent something back to us. Failed means something went wrong and the transport doesn't have to tell you what went wrong. Presumably it will have logged information about the error. All the higher level software needs to know is that this RPC failed, that we were not able to get a response back. And if it failed, you should assume that this session will never work again. You can try again if you want, but it's pretty likely that if you try again, that's going to immediately fail as well. So you should assume that once you have gotten failed back, the session associated with that request is bogus. You should probably throw it away and open a new one if you want to communicate with this server again. Ankara, you look horrified.
I'm a little confused. When you're sending a request, is this a request like a read? And if so, if a read failed because an object was not found, why does that mean that the session has expired?
Ah, right. So you said the question is, if we send a request like a read request and the read fails because, say, the object was not found, why would that cause this to fail and expire the session? And the answer is it doesn't. Failed only gets called if we couldn't get a response back from the server.
Oh, okay.
So there's nothing in the response buffer.
Failed,
It's basically a transport level failure of some sort. Even if we get a response back, the response packet may contain error information, and we don't have to throw away the session in that case.
So how does the client know that it's failed? Or, I mean, it's like a timeout that failed?
How does the client know? You mean, like, how does that information percolate back up here? I'll show you in a bit. Hang on, we'll get to that.
Not sure what the question is. How does the transport layer on the client side know when to fail basically when to decide that it has failed to receive a response? Is it timeout based?
How does the transport layer on the client side know that it should fail? Typically, there's timeouts of various sorts in each of the transports if they can't get a response out of a server in a certain amount of time. And they try various steps for that. But again, because we have this very powerful retry mechanism above it, it's actually okay. Our current transports are kind of cautious and they try and do a lot of internal recovery. That's because they were built a long time ago before we had this retry mechanism. Today, I'm not sure we would need to put as much complexity into the transports. We could probably do much simpler things. Just fail. As long as it doesn't happen very often, then it's probably easier just to kick it all upstairs and let the wrapper infrastructure handle it, which can do a pretty good job of that. Okay, so some other notes, which is that transport get session is not allowed to ever throw an error. It must succeed, and in some sense succeed. And send request may not throw an error, and cancel request may not throw an error. So there are no errors. You should not have to worry about catching any errors coming out of the transport here. All of these things will turn into calls to failed. So for example, if a transport can't actually open a session, it actually returns a special object called a fail session. That's a class that does, whenever its send request method gets called, it simply immediately calls failed on the notifier before it returns. Just kick it up. And similarly, if you get an error while sending a request, don't generate an error there. Just log your message and call the failed method. So again, we're pushing all the error handling into one place, which is the code that sees this failure, as opposed to everybody that calls send request having to have signal handlers and be prepared for error conditions. Yep.
Only one session is created to the single server, or the session is associated with something else?
There's only one session created for a server. It doesn't have to be the case. Probably most of the time that's true. But there's no particular reason why that has to be. That's just an optimization, to avoid overhead. But RAMCloud would work fine. You could create a new session for every RPC, for example. That just wouldn't be very efficient. But in practice, for example, serverless keeps one session for each server in the cluster, and probably that same session will get used, that'll get shared and used by everybody in the server. Yeah?
Why not pass RPC notifier to the get session function? Because in the second and third function, you will pass the RPC notifier.
Why not pass the RPC notifier here? Because typically the sessions are being managed at a higher level. And these things don't even do RPCs. They're just managing data. So we don't necessarily even have an RPC. At the time we create the session, we don't have a particular RPC yet. A different RPC could use the same transport. Yeah. But so it's sort of simpler also that now we only have to pass the notifiers into these functions related to specific RPCs. See, this is not related to any one RPC in particular. Satoshi?
Yeah, is it possible to use multiple transports for
multiple transports for a single RPC?
Yeah,
no. So one RPC uses one transport. A single server could support multiple transports, and it might be that at different times, different RPCs would arrive on different transports. That's possible, but each RPC at any given time uses one transport. However, if you start an RPC and it fails, when you retry, you might actually use a different transport the second time. Ankita.
Related question. Do you have any thoughts on whether the whole idea of pushing errors into one place would have caused disadvantage in terms of latency?
Question is, does concentrating the errors into one place hurt in terms of latency? I actually suspect it helps in terms of latency. In particular, if you don't have to have error handling spread all over. That error handling is likely, like, I don't have to check for errors here. I don't have to check for errors here. And so there's less code in these places, which is, in the best case, that won't impact anything. But in the worst case, it will be slower if we had all those extra checks.
But those checks will be called, or those error-throwing things will be called. The catches will be called only if there is an error, but you catch it earlier rather than later. Because in this case, you go one step ahead, you create a session, then...
This gets back to Benham's question that if you threw errors sooner, you could catch the errors sooner. And so, maybe that would do things a little bit faster. But again, these calls tend to follow each other so quickly. And furthermore, you expect errors to be infrequent, right? We hope that our performance of the system is not determined by the speed of how we handle errors, but rather the speed when we don't have errors to handle. But I think, in general, if you get code out, if you can take out code, that's at worst, the performance will stay the same. I bet most of the time when you do that, performance is going to get faster.
That would happen only if you have a very good network underlying, right? If the network is a bad network, then it's going to drop a lot of packets and then...
The comment is that, well, if we have a really crappy network, it's going to drop a lot of packets and we're going to do a lot of error handling, right? And so if that happens, you would want a transport that handled those errors as efficiently as possible. And you probably want to do the error handling down inside the transport. So those would not even propagate up to these higher levels. Right? Of course, most of today's networks, I think we can generally assume, are quite reliable, that the drop rates are very, very low on packets. And so you don't mind doing a little bit of extra work when the drops happen. What you're more concerned about is the normal success case. Okay, good so far? All right, so now we can start moving into the wrapper structure. Let's see, get rid of the client APIs. So this is a little more complicated, so I'm curious to see how well this will go over. We'll see. All right, so I've already talked about the RPC notifiers. This is a really simple class. All it does is define these two methods, and these are virtual methods. It does not even implement the methods. It just defines the interface of those two methods. So that's all there is for that class. And so you could have argued I could have just put that into RPC wrappers. Maybe I should have just done that, but I thought since the transport doesn't need to know about this, I'll separate that off in case, I don't know, maybe someday later on we want to build some wholly different RPC system that does things in a totally different way. Then it could make some other class that's a subclass of RPC notifier and not have to, we wouldn't have a conflict between that and RPC wrapper. So almost all the interesting stuff happens in RPC wrapper. The idea is that RPC wrapper has stuff that's common to all RPCs. So the goal was to get as much stuff there. And then these classes, these specialize it a little bit for these different groups of RPCs. And I'll talk about how each one of these does things a little bit differently. And so what you're going to see is that there are a few methods that these classes define which the RPC wrapper class invokes at various points. They're basically hooks into various guts of the RPC wrapper class. Like, for example, if we get a transport level failure, what do we do? Well, that's going to be done very differently in the case of each of these. And so they each have a method that RPC wrapper will call to deal with the loss of a session. Okay, and then the last layer up here, these are just classes, one per RPC. And the idea is that all these classes do is to do marshalling and unmarshalling. All they really do is to copy arguments into a request buffer and then copy results out of a response buffer. And essentially everything else, other than that, all the others, the retries and all that kind of stuff, is down here in the blue classes. Okay, so let me talk a little bit about what's in RPC wrapper. So first, what variables are there in an RPC wrapper object? And there are 4 main ones and a couple of other minor ones I won't mention. So the first thing is there's request and response buffers. So what's interesting is that, remember, RPC wrapper is actually a subclass of RPC notifier. So when we call send request, we pass it in a request and a response and a notifier. But actually, these buffers are actually inside this object. Actually stored, in almost all cases, they're stored inside the object. But transport isn't allowed to know about that. It doesn't need to know where they are. All it needs is the request, the response, and the notifier. And you could have other systems where you don't store them in there. But in fact, we do. It also has a session. It keeps track of whatever session it used to send the request. That's needed, for example, if it needs to retry later on, it can use that same session object. And then it has, maybe the most important thing is there's a state variable that says, what's the current state of the request? And let me just put up all the values for that. So there's not started. I think most of these are going to be self-explanatory. There's in progress. There is finished. There's failed, canceled, and retry. So I'll talk about the basics and then fill in the others as we go. But obviously, it starts off when you create a new object. It's not started. And then when you initiate the RPC and do the send on it, then it turns it in progress. And if it finishes successfully, it'll go into finished state. And all these others I'll come back to in a bit. So these methods are implemented by RPC wrapper. They're completed and failed methods. And all they do is just set the status to either finished or failed. Really trivial, nothing more than that. So when the transport calls up to us, we record information, but we don't notify higher level software. We just set up a state flag inside the notifier object, or inside the RPC wrapper object. So all the interesting stuff, or almost all the interesting stuff, happens in isReady. If you look at the code for RPC wrapper, probably half of the file is this one, is the body of that one method. So let me just walk through a little bit of some of the things it does. I'm not going to go through everything. You can read the code and see all of that. But so first thing is, if the state is in progress, it just returns immediately. So all the interesting stuff happens once the transport has called us to let us know whether it either succeeded or either we got a response back or we didn't get a response back. So then what if it's finished? So then one of the things that isReady does is it makes sure we have a valid header in the response. For example, there has to be at least enough information in the response to have there's a status word at the beginning of every response that says did it succeed or has an error code. And actually, the individual RPCs will tell us how long of a header that particular RPC needs. Each one expects a certain amount of response back. And so the RPC wrapper code will check and make sure we have a long enough header to meet the needs, response header to meet the needs of this RPC. So that's mostly bookkeeping stuff. But then after that, it then extracts the header and it checks the status field in the header. And if the status is OK, that's of course what we hope will almost always happen, then we're done, we return. So we return true in this case. And you can see now, remember we got here because the client code called the isReady method on one of these objects, but in fact isReady is actually implemented in RPC wrapper. So that called in, and we've gotten a response back. It has a header. The status says this RPC completed normally, and so then we can return back to higher level software. So the next thing is, what if the status in the response is status retry? So we handle that here. So any server can, anytime it wants, in handling an RPC, it can just return status retry. And then in this code, what happens is that we'll compute the retry time. And change the status. So now the status of the wrapper object will become retry. And the time we want to retry, it's the clock ticks time, RDTSC ticks time, will be stored in here. I didn't actually include that in the list here, but the retry time will be included in there. What if we get some other error? If this happens, then we call a method called checkStatus. So this method is pure virtual on the RPC wrapper object, and it's actually implemented by these higher level objects. Well, actually, it's not pure virtual. It's a default implementation that does nothing. But these objects, I believe all of them override that method. So they can do their own error checks and handle certain errors. And I'll show you in a bit how that happens. Yeah. Yeah, actually, I think it was mostly for testing. It was really convenient to be able to test things without all these things. And also, there are a couple of actual RPCs that have their own pathways down in here that don't use one of these three things. Actually, there are a few red objects that are direct descendants of RPC wrapper. They're mostly sort of weird outlier RPCs. Right. So the idea of this is that this method can return either true or false, indicating whether, in some cases, the higher level software will restart the RPC. And I forget whether it returns true or false to indicate that. But in one situation, it means the RPC is restarted, so we're back in progress state. And then we would just return back again, and the RPC is running again. Because, for example, somebody reinitiated it. Or if the error is an unrecoverable error, or the higher level software doesn't know, these wrappers don't know what to do with it, then we just leave the error there and call the RPC complete. And then these top level wrappers will typically check for errors. They have to check for errors of their own as well. So there's certain well-defined errors we can handle here. Others have to get handled up at the red level. Running out of space. guess I'll continue on this board. So working through the various states of the RPCs. We've done in progress, we've done finished. What if the state is retry? Then we check the retry time. And if that time is reached, then we start the RPC again, send it again. And then the last case is if the state is failed. This is a case where we call another hook method. So call handle transport error. And typically, this method will actually be implemented by one of these higher level classes. And then it will do a retry. And the reason that has to be reflected up is because you're going to do retries in very different ways. Like, for example, if we have a transport error with the coordinator, we're going to have to go and figure out where the next coordinator actually lives, and then open up a new session to that coordinator. Whereas if it's server ID RPC wrapper, that transport failed, we're going to handle that differently by going to the server list and flushing entries in there. And if it's object RPC wrapper, we're going to have to actually flush this session associated with certain objects. So these all get handled in different ways, and that's why there's a hook method for each of those. Yep.
Clarification on retry. Since the retry is happening inside the isReady method, does that mean retries will not happen unless isReady is called?
Question is, will retries happen if isReady is not called? The answer is no. Nope. You can't make progress without calling. You really have to do two things to make progress. You have to call the polar, and you have to call isReady. No RPC will make progress if you don't call the polar. A given RPC can't really make progress, can't retry, unless you call it isReady. One of the tricky things was trying to figure out how do we make these retries happen? Who does them? And can we find a central point that will cause all the retries to happen? And I realized that isReady actually is actually the fundamental heart of the RPC. Everybody calls isReady sooner or later. If you call wait, for example, it automatically calls isReady for you. And so that's why the retry stuff happens there. All right, so that's mostly what happens. That's a quick summary of what happens in the isReady method. And then there's a few other methods in RPC wrapper, mostly not too interesting. One method is a method called wait internal. This is the, you can think of this as the main wait method. The individual RPCs, in many cases, have to define their own specific wait methods because wait returns results, and those results can be different for different RPCs. And so actually, when you do a wait, what you want to do is there's sort of some standard stuff to wait for the RPC to finish, and then these wrappers have to pull the results out and return those. Well, wait internal does all the shared work. Basically, it's just a loop that calls isReady, and then the polar. So it's just a convenience to have that in one place. It gets called by higher level wait methods to do the low level waiting stuff. And there's a few other methods in RPC wrapper. So there's a cancel method. I'm not going to talk much about that. It just sort of does the obvious thing, change the state to canceled, and actually first calls the transport to cancel this using the session object to cancel in the transport, and then it sets the state of this object to canceled. And by the way, if you cancel an RPC and then you try and wait for it, in one of these methods, it will signal you. When you try and wait for it, it'll say, you can't wait for this RPC because it was canceled. In other words, we can't return you a meaningful result. Questions so far? We're actually most of the way done here. Now I just want to tell you a little bit about what happens in these higher level classes to get a sense of what specializations they have. So I think I'll use this board for that. I have to say, in terms of class design, this was the most like a jigsaw puzzle I've ever done in terms of trying to find classes where the pieces all fit together. You don't have to duplicate code in many places, and everything happens just once, and they all kind of fit together right. It ended up being, again, a little more complicated than I would have liked in terms of number of classes, but it was fun how all these intricate pieces fit together, and as a result, things like asynchronous RPCs were all really simple. Okay, so let's start. This object RPC wrapper. So this is used for all RPCs that must go to the server that stores a particular object. So based on the table ID and the primary key of an object, we have to look up a server, find the server for that, send it to that server. And if the thing fails, we have to keep hunting for the server for that object and keep redirecting the RPC to the right server until eventually we find the server and it processes it. So some of the things that this class does is that it calls the object finder class to get a session. Remember, object finder maps is the central class on clients that tries to keep track of where all the various tablets are stored in the cluster. And so given a table ID and an object key, it will give you back a session for that. And then it has a handle transport error method. So this gets called by RPC wrapper if the transport fails in some way. And what this does is that it discards the session. In fact, not only does it discard its copy of the session, but it calls object finder and says, you got a bogus session, throw your session away, make a new session next time. And then it will basically retry the RPC. So retry will go back to object finder to get a new session, and then it'll start the RPC all over again. And of course, the object may be on a different server at this point. And then the last thing is in check status. Check status is the method that gets called by RPC wrapper when an RPC response arrives and it has a response status from the server that's something other than status OK or status retry, some other error condition. And so it looks for just one. It looks for the status unknown tablet. This is a status that's returned when you send a request to a server. You say, I want table ID 47 and primary key foo, and the server says, love to help you, friend, but I actually don't store that table. Sorry, don't know. I don't know where it is, but it's not me. And so when this happens, then the object RPC wrapper class calls back into object finder and says, dear Ms. Object Finder, I'm afraid you are a little confused. You gave me a session for this table, and the server doesn't know what's going on. So you've got some bad information. And so what will happen is that the object finder will flush its state for that table. Including the session, but also, in fact, it'll flush all knowledge about that table. It'll assume, guess I was wrong. I'm just going to forget this table ever existed. And then you retry, and then we'll call back into Object Finder to get information about the table. And now, since Object Finder does not have any local table state, it will go out to the coordinator and ask the coordinator, where is this table stored? And then it'll get fresh state and fill in its table, open new session, and give that session back again. So this handles a situation where an object is moved from one server to another. It'll automatically, we'll find it transparently. And we'll keep chasing until we eventually find the server that has that object. Okay so far? Okay, so that's the object RPC wrapper. That's basically all the code that's in here. Just those little specializations. Ankara.
Is it possible that this could happen multiple times if a recovery is currently going on for the tablet?
Could this happen multiple times? Absolutely, sure. Yeah, if a machine's being recovered, you could have a series of crashes. Yeah, there's no, you can't a priori upper bound how many times you might have to do this. Now, we would hope in practice you wouldn't do this more than You wouldn't often do it more than once per RPC, but
Okay,
you
the
could.
question being, would it make sense to have some sort of a back-off if the tablet is currently recovering?
Would it make sense to have a back-off if the tablet is recovering? Yes. You can imagine implementing that a couple of different ways. One simple way to do that would be there's an RPC to the coordinator that gets made here to fetch the tablet state. The coordinator could refuse to return any information about that tablet state until it's actually fully recovered and ready for service. And so the coordinator could respond to that RPC with a status retry. Or alternatively, the coordinator could respond right away, and then we will go and try and talk to the master. But the master is probably still in the middle of recovery and can't actually service the tablet. And so then the master would return status retry to us. That might be better because then we offload the coordinator. So, but you have your choice. But again, since any RPC can do retries, can ask for retry, none of this mechanism really depends on that at all. By the way, in general, for people, as you're modifying RAMCloud, we should be using retries more than we do. This is a relatively late sort of realization that we want to do a lot of retries. And I think right now we try and handle too many things without retrying and get extra complexity, when it would be easier just to send back a retry request. Okay, that's object RPC wrapper. Let's see, maybe I'll do the next one over here. Next one is server ID RPC wrapper. So this is used for communication between RAMCloud servers. Typically, clients would typically never invoke this. And what it says is that we want to talk to a server with a particular ID. And these server IDs, by the way, are unique. That is, if a server crashes and restarts, it always gets a new ID. An ID is never reused once that server crashes. All right, so this one it's actually in some ways similar to object RPC wrapper, except that instead of invoking object finder to get a session, it calls server list to get a session for the request. And then it also handles both of those two hook cases. So if we had a transport failure, so let's handle transport error. It handles this a little bit differently. What it does is that it flushes the session for that server and then retries. And the way it flushes the session is it throws away its own copy, pointer to the session, and then also calls serverless. It says, bogus session, throw away anything you had cached for that server. So the next time it retries, the serverless will attempt to open a new session to that server. There's one additional twist, though. Well, actually, there's two additional twists. One is that I ended up adding code here that if we're having errors repeatedly to the same server, we actually start backing off eventually. That is delay. The main reason for this was that errors were causing log messages. And so when a server went down, the log would just get completely deluged with messages because it's retrying every 5 microseconds and then trying to log another message about it. So after a couple of failures, it starts backing off and only retrying every second or two. It's basically just to cut down on log chatter. But then the last thing is that there's one special case here. We'll keep retrying for the server forever as long as the server's in the cluster. But if the server has crashed, and we can figure that out by asking the server list, is this server still part of the cluster? If the server is crashed, then we stop retrying. And this will cause an error to be signaled in the wait method. If the server's crashed, wait will signal server not in cluster anymore. That's basically the only sort of low-level error that can happen from the server ID RPC wrapper. So anybody that invokes a server-to-server RPC, you do have to be prepared to catch this one error, which is that the server you're trying to talk to is no longer in the cluster. We can't, it's not like object RPC where we can redirect to the new server that holds the object, because once the server crashes, that ID will never be used again. There's no substitute server for server ID. So the caller has to know what to do if you can't talk to that server anymore. Like, for example, in the case of the replica manager, if a backup goes down, then it realizes, I'm going to have to re-replicate this segment on other machines. And so then it will change its data structure, then it will retry its replication with some new server ID. And then the other issue is this, it's called check status. Again, this is an error happened. An error happened that wasn't status OK and wasn't status retry. Are there any kinds of retries we want to do here? And the answer is yes. There's one, this is kind of a weird special case, but there's one error called status wrong server. The issue is that in RAMCloud, it's possible, imagine we have a server running in the cluster, and it crashes, and a new server takes its place. That new server may actually respond to the same service locator as the old server. That is, it may be listening on the same port. And so it's possible we could be trying to talk to the old server. We get a transport error. We back off. We don't yet know the server's crashed. We haven't found that out yet. We retry, so we open up a new connection, new session, and it turns out we're now actually talking to a different server. Well, the server will check the server ID we're trying to talk to, and if it's not the server we meant, then it will return this back. It's kind of analogous to the status tablet not found request. And so if this happens, then we know this session can't really work for us, and so we do the same thing. We flush the session and retry. And eventually we'll detect that the server's crashed. Information will eventually get to us. Somebody will find out that old server's crashed, and we'll be told about it. And then we'll figure out the same server crash thing. We'll discover the server's crashed, and we'll abort the thing.
So the identifier that we use to get the servers, it can't differentiate between the new server and the old server?
Our server IDs are unique. The problem is that they may listen on the same port. A new server may listen on the same port as the old server, and so the service locator we use to contact that server could be the same.
The service locator doesn't actually encode the information about the server ID?
It's not unique, that's right.
I see.
That's actually an interesting possibility, though. I hadn't thought about that. Could you actually? No, typically we don't want to have instance-specific information in the service locator. Because, for example, when you start up a server, you tell it what locator to use, but you don't know what its ID is, so you couldn't include that in the ID.
So the service locator is specific to a particular physical machine?
A service locator, yeah, sort of like a port and a machine, right?
Okay. So if the data from, say, server ID 1 gets recovered on server IDs 2, 3, 4, and then server 1 comes back up and now has new data, it would still have the same service locator as the old.
It could have the same server. It would not have the same server ID. It would not be server 1 anymore. It might be server 10.
It might be 10, but it will.
But it would be listening on that same locator.
I see.
Yeah. Yeah, locators are not unique.
The locators are not unique only for the same server, for the same machine, right?
Yeah, if you're on different machines, probably the locator is different. Yeah. But for all of our existing ones, that's true. But I can imagine networking technologies where that wouldn't necessarily be true. Who knows? If you had some sort of global network port that you listen on, with a centralized network manager, it might reassign that same logical port number to somebody else. I don't know if that'll ever happen. None of our transports do it today.
We'd need only one to have that service locator, right?
Coming at one time,
At a given point in time.
at a given point in time, probably only one server can listen on a locator. Yeah. Okay. And then I think I'm just going to reuse the same space for the coordinator RPCs, and then we're just about done. Then I'm just going to show you a quick RPC example, and we'll be done. So for a coordinator RPC wrapper, this is used, obviously, for RPCs going to the coordinator. There. Don't you think this documentation tells you things that are not obvious from the code here? Those of you that heard me comment about that on your comments. No.
Well, it could be the case that these are used by the coordinator, not the other people.
I see. I see. Anyhow, it's used for communication with the coordinator. So this calls coordinator session to get a session. And then it also has a handle transport error. And when that gets called, it flushes the session. And that includes calling coordinator session to flush its internal, because coordinator session opens a session and then caches that forever. Well, this will throw away that cached copy. And then we retry. And then when we retry, we'll call coordinator session again to get the session, and the coordinator session will not have a session. And so now it will have to go out and figure out where the coordinator is. For example, right now it will go to log cabin, look up the cluster data area in log cabin, see who the lead coordinator is, and that coordinator will have left its service locator sitting in log cabin. So coordinator session will grab that service locator and then use that to open a session. And that's it. Questions about any of these things? The last thing I want to do is just show you, I'm going to show you the actual code that defines the create table RPC, so you can see what you have to do if you want to define at least the client side of a new RPC. Any other questions on any of this stuff first?
Do you have any comment where the thread dispatcher occurs?
Any, sorry, the question is any
Dispatching thread.
where does dispatching occur?
Yeah. Dispatching thread.
Dispatching threads. So this doesn't really say much about threads. I will say that, so all of this stuff, for example, will happen within one thread.
But it's ready, there might be a.
So actually on servers, the transports could be running in a different thread. And then they would communicate back by setting bits in this. One of the advantages of this particular interface is it's really simple, so it's thread safe. That is, you can have a transport running in one thread that's calling the completed or failed method to just set flags here. And then another thread can be testing those flags and manipulating things. So this particular interface happens to be thread safe. But the rest of this doesn't really say anything about threads one way or the other. Now, in our normal client use, if you're using this RAMCloud object to invoke RPCs, we assume the RAMCloud object is single-threaded right now. We do not, that's not thread safe. And so if you had multiple client threads that wanted to invoke RAMCloud operations, you'd create a separate RAMCloud object, basically a separate cluster connection for each of the threads, and they would use their own object. That's potentially a not great design decision. We actually didn't think about this at all initially, and when Diego and Ryan were at Facebook one summer, they needed multiple threads, and so they got that working very quickly. But at some point, we might want to come up with a better multi-threaded approach on the clients, where you don't have to create a new RAMCloud object. Ankita?
Sort of related question. In all the transports that you've drawn there, is invoked the one that Diego Ryan implemented during their project, like for the course, and are the others pulled off the shelf, or are they all written by us?
Our question is, where did these transports come from? So they were all written by us. Actually, Diego and Ryan didn't write any of these for this course they took a few years ago where they were doing some experiments. I think invoked was the first one written. Steve wrote that. That was supposed to be an extremely quick and dirty transport that wouldn't last long, and surely we would throw it away and replace it with something better. Fast was supposed to be the long-term, beautiful transport. Ryan spent actually Diego spent like 3 months working on it, built a Python prototype of it, and then decided he didn't actually want to write the C code for it. So then he went away for the summer, and Ryan actually implemented the C++ code for Fast. But this one has always been kind of complex and quirky, and it's never really worked as well as invoked. And so and in fact, ironically, it is not our fastest transport. So it doesn't even live up to its name. Note to self, never name anything fast again. It's a jinx. And then TCP transport, actually somebody else implemented a first version, then I rewrote that. I wanted to have kind of a reference transport that people could use that didn't have any special hardware at all. So what Ryan and Diego did in their class work is they implemented an Ethernet driver for this, and then I think Diego implemented another transport called, I think it was called unreliable transport, that used raw Ethernet packet to not do any sort of retry or flow control. If an error happened, the system would just crash. They were trying to do that, I think, to get not to exceed performance numbers. But I don't think it was actually any faster than InfRC.
So the ... refers to nothing else.
Today, actually, I don't think we have the code for unreliable anymore. I think at some point I was having to upgrade transports for new APIs, and I asked Diego if he minded if I just deleted unreliable. So I think that's gone now. Yeah, so the ... is an empty set. But we need, actually, this is a gap that needs to be filled.
Is it possible to assign multiple threads for different transport and then dispatch different RPC to the different?
Is it possible, let's see if I'm going to paraphrase your question, is it possible to use different transports for communicating with different servers? So some RPCs would go on one transport, others would go on another transport. Yes. Right now, you cannot, there's no mechanism to tell an RPC which transport to use. We don't have any interface for that. I suppose we could potentially add that in. Instead, that's all decided by, for example, when you call coordinator session or server list, it's decided down in there. But an individual server, for example, can say that it supports multiple transports.
Okay, in addition, that it is possible to assign different threads or different.
Could you have different threads for different transports? Possibly. I'd have to think about that. We don't do that currently.
Yeah, if we assign a different RPC for the different transport, then the multiple transport, multiple threads for different transport makes things faster.
It's possible. I would guess that typically for any given server, there's probably one transport that's better than the others. And so you might as well use the best one available and have everybody use the same transport. But so we haven't really thought about that, but it's possible that something like that could be done. I don't think we would support that very cleanly right now. So let me just show you the code for create table. This is a really, create table is about the simplest possible RPC. So other ones, some of them get a little bit more complicated than this, but typically not a whole lot more complicated. Okay, so this is the class definition for create table RPC. And so you can see it's a subclass of coordinator RPC wrapper, since create table RPCs have to go to the coordinator. And then all it does is declare the constructor for this class, the destructor for the class, and then a wait method that returns this uint64 type. Okay, so this class has no data in itself. The data is all in the superclasses like coordinator RPC wrapper. Then the methods. So here is this is the synchronous method for create table. And you can see all that happens here is that we construct an RPC object and then call wait and return the value. And again, that's typical for the synchronous methods. Typically, that's all they do. So the interesting stuff is down in the other two methods. Let's see if I can get them both on the screen at the same time. Yes, barely. Okay, so this is the constructor for create table RPC, and again you can see it takes the same arguments as the synchronous method plus a pointer to our overall RAMCloud object. And so it calls the constructor for the superclass. And this is mostly uninteresting, except that in calling the constructor, it tells the superclass how big of a response we're expecting. And that's so that RPC wrapper can automatically check when the response comes back to make sure that we have a big enough response. So we don't have to have additional checks in here. We can just assume that if we survive, if we're still alive, we've actually got a valid response with a header that's as long as we need. We didn't get short-sheeted by the server. So then all that happens in here is we need to fill in the fields of the request header. And so there's a method. This is a templated method provided by, I think, RPC wrapper called alloc header that just basically says it's going to allocate enough space in the request buffer for our header, which happens to have this type, wire format create table, and return us a pointer to that. So we get the header, and then we just fill in the fields. This is the fields of our RPC. We fill in the length of the name and the server span, and then we copy the name after the header. So the actual RPC has this little header with 2 fields in it, and then after it's fixed size, and there's a variable length chunk after that in the buffer that has the actual string characters for the name. And this code here allocates more space in the buffer. That's what this new does. Allocates a character array of length, and then it copies the name, mem copies the name into that. And then finally, we invoke the send method. And actually, the send method is defined by the class, by the coordinator RPC wrapper class. That's the method that calls coordinator session to get the session, and then calls the send method on that session. So far, so good. So again, it fills in the header data and sends the RPC. And typically, that's what all RPCs do. They just copy data into the packet and send it. So the nice thing about this is there's nothing, everything here has to be here. That is, this is the only method, the only place where we have specific enough information to do all this, so nobody else can do it for us. And we have no other overhead. Nothing to worry about asynchronous RPCs, nothing to worry about any of these error handlings, the retries for the coordinator, all taken care of elsewhere. Yeah, Henry. Is this, sorry? This is a placement new on the request buffer, right? Pardon? So remember, the buffer is in the RPC wrapper object, which is our superclass. So that was initialized as part of constructing the superclass, and this request is simply a reference to the. That's an instance variable in this create table RPC object. Okay, so then if we want to wait, then I mentioned there's this wait internal method that's implemented in the RPC wrapper class. So we call that, and actually you have to pass into that the name of the dispatch object that has the poller that you can poll on. And then at this point, once this returns, if we didn't get a suitable header, return back wait internal will already have signaled that for us. So we don't have to worry about that. So we can assume we've got a reasonable, thing actually came back with a reasonable header. And so in fact, we can get access to that. Actually, we call get response header as a method on the RPC wrapper object that will return us a pointer to a header in the response of the right type. And then we check the status field in that. And if for some reason there's some other exception that hasn't already been caught, then we immediately throw that exception. If not, then we just pull the table ID out of the header and return it. Okay, so this is pretty typical for a wait method. Do the real waiting, grab the header. If there's an error we don't know about, throw an exception, then just pull things out of the result and return them. So to write a new RPC, it's not totally trivial. You have to write 4 chunks of code. You have to first write a chunk of code declaring the class, typically cut and paste and then modify. And then you have to write the object constructor, the wait method, and finally the create table method. There's one exception to that, which is that in many cases, if there are RPCs that do not return any results, then you don't need to write a specific wait method for that RPC. There's actually a generic wait method you can call that does all the generic stuff. It will check for a status and throw an exception, but it doesn't return any results. There's no, if you're not expecting any information back. And let me see if I can find one of those. I think it's called simple wait. There it is. Right, so the drop table RPC takes a table name we want to delete, but it doesn't return any result. The table's gone. There's no information to return. And so the wait method for this is simply defined. Basically, it's inline replaced with a call to simple wait, which is one of the methods defined in one of those wrapper classes. That's a shared method.
This didn't exist 2 years ago, did it?
Pardon?
I don't remember this existing about 1 or 2 years ago.
It did not exist when you were doing all the work to build multi-reads and multi-writes initially, for example. Yes, this probably would have made your life a little easier back then. Actually, multi-reads and multi-writes have their own interesting, they have a more complex wrapper structure because they can send out batches of RPCs and get responses back, and then they have to send many RPCs, a series of RPCs to do their job. But they actually fit reasonably well with this structure. Okay, I think I've covered everything I want. I've not talked at all about the server side. The server side is actually much easier. You just write a method that takes a header, takes a request header and response header, it does the thing and fills in the response. It's really a lot easier than it doesn't have to worry about all this multi-layer wrapper structure stuff on the server side. Any questions I haven't answered? I'm also curious, any flaws, what things about this, if you look at this critically, are there things you don't like about this? And if so, I'm curious what those are. Besides the fact that I will plead guilty on that there's more classes there in that hierarchy than I would like. But do you see other problems with this?
I don't know if that's a problem with the design or not. But I assume maybe we could do better if we go multi-threaded. All the things are happening in one thread.
Could you go better multi-threaded? Better in what sense?
In the sense of reducing the overhead of the software for the latency.
Could you reduce the overhead? My concern is that going multi-threaded would probably increase the overhead because you'd have additional, if you have to do thread transitions, those are quite expensive. So actually one of the goals here was we want to do everything within one thread. So on the client side, for example, this whole thing happens in one thread. Everything from the top-level RPC calls, calling in the polar, running the transports, it all happens. We don't have to pass information between threads. Because the problem is that requires synchronization, it requires cache misses to move information from one thread's cache to another. And so my suspicion is that for lowest latency, you probably don't want to switch threads.
For the client side, there could be in our cluster there's like 8 cores per machine, right? And for the client we're only burning 1 or 2 cores at a time. So.
Right. The question, repeat the question is that we have 8 cores on our client machines and this is only using 1 core. So wouldn't it be better to try and use all of the cores at once?
Oh, but it's more. And you have the flexibility to.
Why would you use more cores unless you get something for it? Besides, so we could maybe waste more core resources and run more slowly. So I mean, I'd be happy to use more cores, but it seems like you want to get something back for it. And the main thing we'd like to get is latency, but I don't think, well, if you could figure out a way to use more cores to get latency, I'd love to hear about it. So far, every time we've tried to use more cores, our latency has gotten worse, not better, like on the server side, for example. But if you could, that would be great. So if you have ideas on that, that would be cool. Other comments? Okay. I think you can turn off the TV and we can stop now. Bye, everybody. See you next week for another RAMCloud show.